Hi, this is Nick from Forward Loop. I'm here to introduce you to Floop, which is a command line tool that lets you work with multiple Linux ARM devices at the same time using the tools and languages that you already know. So today, to show you how that all works, I'm actually going to be running several different applications on 3 Orange Pis and 1 Raspberry Pi. So for these applications, we actually have 3 different operating systems that are running across these different devices. We have on the Orange Pis Armbian Stretch and Armbian Xenial, and then on the Raspberry Pis we have Raspbian Stretch Lite. So let's look at the applications that we're actually going to be running on there. So these are relatively simple applications that we're going to be running. They're just Hello World applications written in 3 different languages. So here we have C++, Python, and Golang. The structure of these 3 applications is roughly the same. We have 2 different Docker files. We have a Docker file for testing, and we have a Docker file for our actual runtime environment. So a lot of the time you would actually want to have different dependencies for testing and for production, so we split those out here. For all 3 applications, we have a function that prints Hello World for our Hello World example. We have a test suite that tests our Hello World function. We kind of assume it will pass, but this is a good test of the application nonetheless. And we have a main routine here that would be just like any main routine that you would have in your production environment. So here, all in one screen, we have these 3 separate applications that do roughly the same thing. So how is it that we actually run these applications on these 4 devices? Well, we use Floop. So Floop relies on a single configuration file. It's actually just here, a 7-line JSON file that lets us define how it is that we interact with these 4 devices. So within this file, we define all of our dependencies that are on our host and all of the folders that would contain all of the application code that we would want to run on the individual devices. So here we can see the actual cores, which are our devices that are defined. So we have cores 0 through 3, so those are our actual devices. And here we have test 0. So test 0 is actually a Docker machine running locally on my laptop. And I'm going to show you how you can run the same code actually just to test it without even having any of these devices. So here we have core 0, which is an Orange Pi, running our C++ example. We have core 1, which is also an Orange Pi, running our Python example. And then we have cores 2 and 3, which are 1 Orange Pi and 1 Raspberry Pi. Both are going to run our Golang example. But actually the core 3 is a Raspberry Pi, so that means that it is an ARM v6 device, which means we need a slightly different Docker file. But if you look again at the application, what that ends up being is just a change of a single line here. So instead of using library Golang, we just use an ARM32v6 image and start from that for building all of this. So we change a single line, runs on Raspberry Pi. And here again is our Docker machine, and we can actually run our Golang example. So we will compile it and run it here on an Orange Pi on ARM v7, on a Raspberry Pi on ARM v6, and on my local machine on Intel x86. So 3 different architectures. So all told, we have 4 different devices, 1 virtual device, 3 different operating systems, 3 different languages, 3 different architectures across 2 different types of hardware, all with 1 tool. And that tool is Floop. So we are going to introduce Floop now. The commands are relatively simple. So in the beginning, we just need to create our devices. So we will create these devices in line with our floop.json. So we just type floop create -v. And here, the -v means it's verbose. So we actually get to see all the commands that are running under the hood. Truth be told, before this example, I actually created these devices because it takes about 10 or 15 minutes to install per device. But once it is installed, you do not need to reinstall it. So here, once it's installed, we check that we have a network connection to all of our devices, and indeed we do, and it succeeds. So now that we have our devices created, we want to get the code actually over there. So we use floop push -v. The V again is for verbose. The push will synchronize the code that we have here in R. So for this example, we're in the project folder. So for our C++ example, we would look in the example/cpp/hello folder for all of our example code, and the same for Python, same for the Go. So we use the push here. Push should synchronize all of the code over to our different devices. And that is what it is doing now. And there we go. We used rsync together with Docker Machine under the hood to synchronize all of that. So the code is now on all of the devices it should be as defined here. So we pushed our C++, our Python, and our Go to our 5 different devices here. We then want to build that. So building means that we actually follow the instructions in our Docker files that we have defined here, again, in our applications. So these are the Docker files, not the test Docker files. We build those. Again, for this example, I've actually pre-built them just because you would need to download and install all of the dependencies that are inside of your Docker files, just like you would with a normal Docker image. So here we're actually using the cache, which is nice. You saw how quickly we actually were able to build and check all of that on these 5 different devices. So now that it's built, we know that it works. We can run the actual example. So run actually will push, will build, and then we'll run. So we enforce pushing, building, and running because we never want to store state. We always want to know what code is exactly on the device. We always want to make sure that it's the newest code, that it's just been built, and that we know exactly what we're running. So we've run this code. You probably saw a couple hello worlds with exclamation points blow by. And if everything goes as planned, we should run these 3 different examples on these 5 different devices. Here we see more of them coming through, and there you have it. So we also want to make sure that we can test it as well. So test is very similar to run, except we use the dockerfile.test, the test Docker file that we can define also here. So let's run our tests and see how they look. Similar to the run examples, I actually built and ran these test examples. So it's using the cache right now. Again, because it takes usually about 10 to 20 minutes, but for each device, you only have to do that roughly 1 time. So all told, to install and get up and running, you need to spend, let's call it 45 minutes to get 1 device up and running, and then you don't have to do that again. So now our tests are running. We saw that they ran in our different languages. As we scroll through, we can see that they all passed, and we're happy with that. Now, if you're watching at home, you probably saw these blow by a little too quickly. So we can look back and see the commands that we ran and the outcomes by running Floop logs. So logs actually will just give us the contents of a file here that is made for your project called floop.log. So floop.log is just a plain text file of the logs that you have. And I prefer to store that with my individual applications to ensure that I know exactly what code was run, so I know what the state of my devices is. Again, to make sure that I'm not storing state, making sure that everything is running correctly. For the logs, for example, if we wanted to look for our hello worlds in there, we can use the -m flag for matches. And there we go. We see lots and lots of hello worlds, the ones that we expected. So the final thing that we can do with Floop is just to check that we're not messing with any of the Docker machines or Docker containers that are running on these devices already. So we can use PS, and that actually just runs Docker PS on all of these different devices. And we see that nothing is running. All of our run cases, our test cases have finished and they have passed. And that is Floop in a nutshell. So again, we've just run C++, Python, and Go across all these different boards, all these different operating systems, all these different architectures. We standardized it. We never stored state, and we always knew exactly what was happening. We had a perfect log of what was going on, and now we can expand upon our example if we want to, for whatever languages we want to use, because this is not actually limited just to C++, Python, and Go. You can actually change these Docker files. You can change the underlying application to run whatever it is that you want and make sure that it's always synchronized across your devices. So if you have more questions, if you have more interest in this, I highly recommend that you check out docs.forward-loop.com to see the official documentation for Floop. If you have any questions, concerns, you find any bugs, you want to raise any issues, you want to request any features, you can find us in the GitHub repo at forwardloopllc/floopcli. Thanks for watching.